Hey, growing enthusiasts. I am back with my final episode for this season of the No-Till Market Garden podcast. Over the years, I've gotten a lot of questions about soil testing. Why is my result from this lab so different than my result from that lab? And why are the recommendations different? For this episode, I talked with Bruce Hoskins, who runs the Soil and Plant Analytical Lab at the University of Maine. It's impossible to cover everything you ever wanted to know about soil testing in an hour, but I think we lay the groundwork here by going over what exactly happens to a soil sample when you send it into a lab for the basic nutrient analysis. Maine seems pretty dedicated to keeping their university soil testing lab open, but I know a lot of land-grant universities have decided to close them, which leaves growers having to decide where to send their samples. For those of you in this situation, I hope this conversation helps answer some of those questions. I also realize that there's some irony in having this conversation about soil testing come at the heels of my conversation with Will Bonzal, who said he has only ever tested his soil once or twice. There are a lot of ways to farm. As Bruce says, soil testing was developed to optimize the economics of farming, to know which nutrients might boost yields and profits, and has also evolved into a tool that we can use to determine the potential of agricultural systems to contribute to nutrient pollution. There's also a role for soil testing to contribute to growing the most nutritious foods, but we don't get into that here. Without further ado, here's Bruce.
Today's episode of the No-Till Market Garden podcast is brought to you by Harnois Greenhouses. For more than 55 years, Harnois Greenhouses has led the way in controlled environment agriculture innovation, partnering with market gardeners and farmers across North America to deliver comprehensive commercial greenhouse solutions. Their mission is clear and steadfast: to pioneer a greener, more resilient future for agriculture. At the heart of their success is a commitment to their community of producers with extensive expertise in design, manufacturing, and installation. Harnois Greenhouses provides the best greenhouse solutions to the grower across North America. Their greenhouses are engineered to face any North American climate, ensuring unparalleled brightness, agronomic performance, faster return on investment, and lasting durability. They're not just building greenhouses, they're creating energy-efficient ecosystems that promote sustainable and profitable agricultural practices. With over 20,000 projects to their name, they're more than a manufacturer, they're a partner. For the initial design to the final installation, Harnois Greenhouses is with you at every step, guaranteeing the success of your venture. Harnois Greenhouses, leader in turnkey solutions for local growers. All right, enjoy the show.
Well, thank you for doing this with me. I know that a lot of listeners have been wanting to have an episode about soil testing, and we could probably have several episodes about soil testing, but I wanted to start with the basics. And you're one of the first people I think of when I think about soil testing, because I started my farming career in Maine, and your name has been associated with the University of Maine soil tests for as long as I can remember. And so I was hoping we could get started with just a little bit about your background, what you do at the University of Maine, and what got you into it.
I'm Bruce Hoskins, and I manage the soil testing program for the University of Maine. I've done that for several decades now. And as with any program, it's evolved quite a bit, certainly over the last, 3-4 decades that I've been here. I became associated with the soil testing program in the early 80s when it was first computerized, the recommendations. And we've evolved considerably since then with some new technologies, certainly analytical equipment has evolved tremendously over that time. And soil testing is been somewhat more standardized than when I first started here. And and we've got new management scenarios like high tunnels, which are completely different. We can do a whole program on that if you want to. So it's been a positive experience overall, and it's really nice to be able to work with growers and gardeners, as well as the research community. We provide the same analytical services to both the research community and the general public. So that's pretty much our mission. And so we can get into any specific questions you have about how it's done. It's kind of a black box to a lot of people, unfortunately.
And I'm always curious about, sort of the personal story. What drew you to soil testing? Were you more of a chemistry person or a agronomy person, or did you just happen to end up working in a lab?
A little of all of those. I was a pretty avid gardener. And crop production has really been my interest. I just kind of, started working in the lab as a technician and kind of worked my way into soil testing through the programming route, actually, and had to learn all about how soils work in a hurry. Took all the soils classes at the university and built on that background and have built the program over the years. It's a really unique coordination between research here through the experiment station and cooperative extension. So extension does quite a bit of work as well. So our lab actually is a hybrid lab between research and extension. That's how we keep one foot in both worlds. It's kind of the classic design of university service labs, that you have a certain set of standard methods that you're running for the research community. You offer that to the general public for a sample fee. You fund your operation that way. So we do fund the vast majority of our operation, including salaries and equipment replacements and everything, through sample fees.
And I do have a question about why fewer and fewer universities are having their own labs. But before we get into that, I want to go back to something that I think is really fundamental to the idea of soil testing. And you and I emailed a little bit about this before, but this idea, my soil chemistry professor always would say, this is an operational definition. And I was hoping you could talk a little bit about the difference between sort of what is an operational definition and how does that matter for interpreting soil tests?
Okay, so we're primarily talking about test methods and the interpretation for that method. Soil testing in general, regardless of where it's done, soil fertility testing, it's an indexing system. It's not an absolute. In chemistry, it's called semi-quantitative analysis. You're not looking at total amount of phosphorus. You're not looking at the total amount of potassium. You're interested in how much of that nutrient bank in the soil is available for plants to take in over the course of a full growing season, for instance. So we try to emulate what plant uptake from the soil. We're developing, and over the last 100 years or so, there's been developed different testing methods in different parts of the country that work best with those with the climate and the chemistry of those soils in that region. So, and within each of those regions, that method has to be calibrated. So it's not enough to know, okay, is 40 pounds per acre of phosphorus, is that not enough? Is that sufficient? Or is it more than you need? And that's what you're talking about. Operational definition is the calibration. How do you, for a specific method that looks at plant available nutrients, how do you determine what the numerical results actually mean? So that's done through soil test calibration, which is done, most of that was done in the 40s, 50s, 60s, up through the 70s, at least on a regional basis. And we do kind of coordinate regionally in our interpretation and recommendation philosophy, because we have standardized on a regional basis our test methodology to make sure everyone's running the same test the same way. Then we can share research data and better interpret the test results on a regional basis. So that's really the operational definition of soil testing. Is we're trying to emulate what plants can take in from the soil.
Yeah, so it's not you have X amount of phosphorus total in your soil. It's you have X amount of phosphorus via the Melic 3 extraction or the modified Morgan extraction. And so you have to take that, into consideration. So that sort of brings me to, and I want to talk a little bit more about this idea of the different extractions. But I think that we could do that if you could walk us through a sample comes into your lab and what is the information that you need from the grower? And then how is that sample processed at your lab? And then how do those results get spit out? And it's fun to hear you say, you were there when they first became computerized. So anyway, just what happens when you get that lab with the information, process it, interpretation.
Okay, so even within each region, there's certain commonalities in the way samples are processed. So what we need from the customer or the grower is obviously your contact information and specifically what you're growing. I mean, we have over 100 different sets of recommendations in our recommendation engine. So we just need to know, is it a general garden? Is it a specific crop like nightshades or vines or greens? So there's different nutrient requirements for each of those groups of plants. And so we need to know, specifically what you're growing so that we can make, specific recommendations to build on what's already in the soil to tell you what you need to add for nitrogen, phosphorus, potassium, or any of the micronutrients, for instance, based on the specific requirements of that. Usually goes by family of plants. So we need to know specifically what you're growing, and then do you have any specific management requirements? Are you rotating through potato crops, for instance, in which case you might want to keep the pH down a little bit? So we take that into account when we're making lime recommendations. So just background information like that. Do you need any special analysis? We have several add-ons. A quick soil health test through a soil respiration test we call our soil biology test, which is just an add-on that we can do within the 1 week that we're running your samples. So that kind of background information. And then once it gets here, our lab is set up to do weekly batches. So whatever we get Monday through Friday is run the following week as a batch. That's most efficient at our scale. So we assign it a reference number, and then we dry the sample down. So all soil fertility testing pretty much nationwide is done on dried and screened or 2 millimeter minus soil. So the sand fraction starts at 2 millimeters and goes down. Anything larger than 2 millimeters, we sieve out and remove, because we're going to homogenize that sample and take a subsample. And we need to have every spoonful of that sample be like every other. So we're doing a representative sampling of what you've sent us that you hopefully have done a representative sampling of in the field, because there's 2 million pounds of soil in an acre. Acre 6 to 7 inches. So then there's a lot of variability. So it's just as important for you to take a good representative sample from several different spots, mix those all together for a good composite for a good overall average. You're taking a representative subsample. We're taking a representative subsample of what you send in. So the drying process, we air dry. If you're going to dry your sample before you send it in, don't oven dry it because that will affect the test results. There's an upper limit of about 95 degrees Fahrenheit, 36 centigrade, above which you're not supposed to dry soil. You lose some of the potassium in the clays that otherwise would be available in the soil test. So we air dried, we sieve it, and then we subsample it for nutrient extraction, we subsample it for pH, and we subsample for organic matter. And, so you want to go into the nuts and bolts of extractions and so forth.
I do. Yeah. I think this audience would be really interested in that. Yeah.
Okay, so the regional differences come in the nutrient extraction. Most places run, pH. You mix it with water, and you let it equilibrate because you're measuring pH of the hydrogen ion activity, which is pH in the water that's in equilibrium with the soil. So we let that equilibrate for about 30 minutes. You take the pH. You measure the pH in water with a pH electrode, and reference electrode. We actually have a pH robot that does 2 samples at a time, reads until it gets a stable reading, spits out the stable pH, moves it on to the next 2. And that's the pH, the soil pH. It shows up on the report as labeled soil pH. That's the pH that you're actually managing for to maintain proper nutrient availability and so forth. What it doesn't tell us precisely is how much acidity there is in the soil that needs to be neutralized to get that pH to an optimal level of, say, 6.5. So to determine that, we add a buffer, it's called a lime buffer solution, just to the soil water mix that we measured pH in. And that draws out all the acidity in the soil, which changes the pH of the buffer solution. And we measure after 30 minutes of contact time what the ending pH is in the buffer. And that tells us exactly how much acidity there is in the soil to be neutralized. And our report that's labeled as lime index, it's just the pH in the lime buffer.
Yeah, so that's a good point. That if one soil that has a pH of 5.5 and another soil that has a pH of 5.5, those might actually take very different amounts of lime to raise the pH to 6.5. And so you are calculating that in the lab. Yeah.
Definitely. Yeah. Right. So that's how it's measured. The more clay content, the more organic matter content there is, the higher the buffering capacity, the more actual acidity there is held in the soil in reserve at the same pH that it would have in equilibrium with water. Hopefully that makes sense. So higher organic matter, higher soils with higher clay content takes more lime to get from 5.5 to 6.5 than it would, a sandier soil or a soil that's lower in organic matter. So that lime buffer takes that into account automatically. And we move on to...
so that's the pH. So then, so the nutrients then,
nutrient extractions. This is where you have regional differences because nutrient chemistry varies quite a bit from region to region, especially with respect to phosphorus and the micronutrients. So here in the Northeast, we have geologically young, naturally acidic soils. So in the Northeast, there are a couple of different, more or less regionally standard extractions. There's the original Morgan extract that's actually still used at Cornell for agronomic crops. That's sodium acetate, has a pH of 4.8, and it's very well buffered. So it's a mildly acidic extraction. Sodium acts as a mass exchanger for the exchangeable cations, calcium, potassium, magnesium, that are held on those negative charge exchange sites in the soil. So you flood the soil with sodium, it knocks those off into the solution, puts itself on in its place. So you're doing a mass exchange of exchangeable cations, nutrient cations, so that they can be measured. It has a mildly acid pH, which extracts some of the phosphorus, but not all of it. So it's specifically designed to avoid phosphorus complexed with aluminum, which we have a lot of active aluminum, reactive aluminum in our soils, our geologically young soils that have a fairly low pH. So that was the original intent, because for annual crops at least, phosphorus bound with aluminum is very marginally available, basically unavailable. So that's what that was originally designed to access, is that fraction of phosphorus that's more readily available in our high aluminum, low pH soils. And because, again, and with the micronutrients, you can also extract, because in that mild acid extract, it solubilizes things, the metals like copper, iron, manganese, and zinc. So those can be all measured at the same time in the same extract.
One nutrient that I know doesn't use these other extractions is boron. So that's always an add-on, right?
Well, boron, it's included. We do extract and measure boron.
You do? Okay, so that's not a separate hot water extraction.
That's the reference method for available boron. Plant available boron.
Okay.
We've just run. Actually, I've run a modified Morgan, which I'm going to talk about in a minute. But we've run Morgan type extract with measured boron, and then we do hot water and just correlate the two. So it makes a difference. So we're estimating, what we're actually reporting is an estimate of hot water extractable boron, which is the standard method for plant available boron, but it's extremely labor intensive. And we used to do that, but we charged, we had to charge for the labor. So it was like $10 just to measure boron. Yeah. So the original Morgan, it has some analytical problems. It tends to salt up the equipment. And the big problem that it has nutrient wise is it's not particularly efficient at extracting potassium from clays. And they figured this out in Vermont in the mid-'60s, where they were seeing no response to added potassium where there should have been, according to the soil test. It tested low, and they'd put on more potassium, and they wouldn't get any more yield. And this alfalfa was a high potassium demand crop that they were studying. And it was heavier clay soil, so they started playing around with different cations, and they settled on ammonium, NH4 with a +1 charge. And ammonium is much more efficient at extracting potassium from clays than is sodium. So they just, that's the modified Morgan, is ammonium acetate, pH 4.8, same pH. They're almost identical in their test results except for potassium. In sandy soils, they both look the same. So, and most of the New England states now use modified Morgan: Maine, Vermont, Massachusetts, Connecticut, and we all kind of standardized our methodology. We don't necessarily standardize our interpretation, but we're close anyway. So that's the Northeast Regional Standard Method. Malick 3 was developed in North Carolina. Adolph Malick did this in the early 80s, and it's a hybrid extract, and it works well with southern, geologically older soils in the South and the Midwest. and it's pretty much the standard methodology for most of the big commercial labs. It's sodium acetate and, ammonium acetate, not sodium, and ammonium fluoride. And that's the big difference with phosphorus. And it's buffered at pH 2.5, so it's a little more acidic than a Morgan-type extract. And it has fluoride, so fluoride in an acid solution will break aluminum phosphate bonds. So you get all kinds of phosphorus coming out in Malic 3 that you don't get in a Morgan-type extract. And that's the question I'm asked most often is, how do you convert? How do you convert? How do you convert? And farm by farm, you can get a reasonable conversion, but, overall, it just doesn't work very well.
It makes more sense, rather than trying to convert, it makes more sense to use the extraction that is
appropriate for your region. Yeah, right. So because you extract so much more phosphorus with the Malic 3, it has an entirely different interpretation set up. It's calibrated. If you're calibrated to Malic 3, you're going to have different, the same numerical results are going to have an entirely different interpretation. Is it not enough? Is it enough? Or is it more than you need? Based on, that's the whole calibration thing is any extract that you choose, you need to run field trials, greenhouse trials, where you vary the soil test level and measure yield, either biomass or uptake or yield and quality. And then you determine at what test level there's a sufficient amount so that if you add more, you don't get any additional yield or any additional improvement in quality, for instance. So each of these extracts is calibrated regionally. Yeah.
I was just going to say the other thing that these soil tests are increasingly being used for is sort of prediction of phosphorus loss as well. So I guess if you have anything to say about that, that would be great.
Right. So that's one of the big changes that I've seen over the decades is, it was mostly these methods were all developed for agronomic or horticultural production. You're after yield improvements and so forth. But, as long as you're doing this and it's relatively cost effective to run a lot of these samples, it's being increasingly used, all of them are increasingly used for environmental purposes and nutrient management regulation purposes. There's correlations between Morgan-type extracts and like water-soluble phosphorus, which is one of the more egregious forms of phosphorus that's most prone to runoff, just water running over the surface into a stream or a lake. And, if it dissolves phosphorus on the way by, that's immediately available for, to cause eutrophication problems. And so there's correlations between that and Morgan. And what we're most concerned about is at the level of which we're considering that point at which you get no additional yield. Okay, that's called the critical test level. If you're above the critical level, and we're going to recommend that you don't apply any more phosphorus. We want to make sure that that correlates well with any of the environmental concerns. And for the most part, where we stop recommending phosphorus is above that test level is where you start to see really some real problems with the potential for phosphorus runoff.
And is that on a report, would that just come back as the optimum range is sort of that critical test level? Okay.
Right. So the top of the optimum range, from there up is where you start to see an increase in the quote unquote environmental hazard, if you will. So, so the other thing that's of concern with phosphorus is what's the capacity of soil to hold phosphorus safely against the surface runoff. And that's where actually the Mehlich 3 comes in very handy, because there's what's called a phosphorus saturation index. And Mehlich works very well to extract, as I said, a lot of aluminum phosphates and iron phosphates. So most of the states who use that on the East Coast, around Chesapeake Bay especially, they measure iron, aluminum, which are your primary binding capacities in the mineral component of the soil, for phosphorus. So they measure iron, aluminum, and phosphorus in the Mehlich 3 extract. You look at the ratio of phosphorus that's there versus the amount of iron and aluminum that was extracted with it, and that tells you, are you close to the binding capacity for phosphorus or not? That's called the phosphorus saturation index, and that's used as a relatively inexpensive and quite effective environmental indicator for phosphorus runoff. So we do run Mehlich 3 here as well, but generally for that purpose. So yeah, more and more soil fertility methods are being rolled into environmental regulations and nutrient management regulations.
Today's episode of the No-Till Market Garden podcast is brought to you by Local Line. Get ahead this year with Local Line. Make the switch to Local Line and grow your farm to new heights. Local Line is the most comprehensive sales software built for farmers and food hubs. Increase your sales and streamline your process with features including e-commerce, inventory management, subscriptions, website builder, online payments, point of sale, and more. Trusted by thousands of farmers around the world, Local Line is the platform you need to take your farm to the next level. Subscriptions start as low as $49 a month, and Local Line never takes a percentage of your sales. Try Local Line today and receive a free premium feature for 1 year using our coupon code NOTILL. That's all caps, all one word, NOTILL. Today's episode is also brought to you by Farmhand. Tired of admin work and technology trouble? You need Farmhand on your team. Farmhand is the all-in-one software platform and virtual assistant built by and for independent farmers. Through a simple text or email to Farmhand, you can instantly offload admin tasks, automate your CSA, update your website, and sell more to your customers. With zero startup costs or long-term commitments, farmers are reporting an average of 6+ hours in time savings and 20% in sales growth each week. Learn more and take the quiz to see how much you can save by partnering with Farmhand at farmhand.partners/no-till. That's farmhand.partners/no-till. All right, back to the show.
Are there since I think listeners are coming from around the country, are there other extractants that are worth mentioning that are commonly used in different labs?
Yeah, well, I've talked mostly about the eastern U.S. Once you get into the arid areas, the high plains and certainly into the desert Southwest, those soils, because of the climate, tend to have naturally high pH. And phosphorus chemistry in a high pH soil is completely different from phosphorus chemistry in an acidic soil. So I've already mentioned that phosphorus is bound by iron and aluminum, but that's in an acidic soil, a soil with a pH below 7. Above 7, phosphorus starts to be bound with calcium. So in the starting with, Colorado, Utah, and down into California and down into the Southwest, they use a completely different extract for phosphorus, which is just sodium bicarbonate, slightly alkaline. It's called the Olson extract. So we're getting more and more samples from outside of our region, and I have to be careful that we're not running our routine Northeast soil test on something that is completely inappropriate for, and we do try to warn customers away from try to use a lab in your own specific area. We can run their regional extract, but I don't have any interpretation for it. That's the problem.
Yeah. So I guess that I have two questions. Why do you think people are sending their samples to you? And then the second question is, if you send your sample to a private lab or just any lab, where do the different labs get their recommendations?
They're supposed to be using the recommendation of the land-grant university in their area. So, but they're pulling samples from all over the country. So they'll go with, like even with the Malic 3 extraction, there's a different interpretation in the more western states than there is in the more eastern states. So a lot of labs are just, they just report results without making recommendations. Some of them do, some of them don't. But hopefully they're using the recommendations of the land grant lab from where the sample was derived. So that is required actually for nutrient management regulations. So I get calls from, consultants, farmers that have tested with a commercial lab, but it's a sample from Maine. And so they're getting a Malic 3 phosphorus, and what do I do with this? Well, there are some conversion tables, but they're very general. Corinne Ketterings at Cornell did a lot of work with the original Morgan, and if you factor in enough factors in the Malic 3 extraction, you include aluminum and iron and, of course, phosphorus and interaction terms and quadratic terms, and it's just this huge brute force regression. You can get fairly close, at least for nutrient management purposes, but down in the range where you would expect a response to added phosphorus, the uncertainty in that relationship is high enough that it doesn't work well. It depends on the purpose that you're using it for.
Okay, so back to what's happening in the lab we went through the pH for the nutrient analyses. It's basically you shake the soil with this extractant, and then you measure the nutrients with various instruments, and then you put it into your computer and hopefully get a regionally relevant recommendation for the specific crop. You mentioned you divide the samples into 3, and the last part is organic matter. So how do you analyze organic matter, and what are some of the different methods for that?
Right. So organic matter is always kind of an indirect measure. Well, as is soil testing in general, but with organic matter especially, most labs are running, if you're going to do, high volume, you can't really run a chemical test on it. Most labs, including ours, we basically dry it down, oven dry, weigh it, and then put it in a muffle furnace and heat it up to 375 centigrade, in our case, or 750 Fahrenheit. For 2 hours once it gets to temperature. So that burns off the organic matter in the soil. You cool it off, you weigh it, and the amount of weight that's lost is proportional to the amount of organic matter that was in the soil. It's quick. You can do it in mass quantities. We do like 120 at a time. And most labs do that. The old chemical method for organic matter that was developed in the 1930s is the Walkley Black, Walkley, Walkley Black method, where you oxidized part of the soil carbon with chromic acid. Nasty stuff. Very colorful when you run the method, but what we've all done, each of us, we've taken like a couple hundred samples from our state. We've run the loss on ignition, we've run the Walkley Black, and you just create a regression equation that the LOI converts to a Walkley Black equivalent organic matter. And the reason we do that is those farms that are still, that are not organic, that are using herbicide application rates are based on organic matter content in the soil, and the organic matter that they're based on is the Walkley Black, the old-fashioned Walkley Black method. But it's probably less and less relevant, certainly for organic production, but at least it gives you a handle on. But see, when you burn off the organic matter, you have to be careful that you're not burning off other constituents that aren't organic matter. So there's always a bias, especially in high clay soils. Even though you're oven drying the sample to drive off the last little bit of moisture, the clays will still hold water between the layers, the lattice layers. So you can't really drive it off at 110 centigrade or 220 degrees Fahrenheit, but it does burn off at 375. So, right. So loss on ignition is what it's called. Most labs do that, and you just go with the uncertainty, especially in heavier clay soils. The other thing that you can do is to take that soil and run an actual total carbon. Now that we have combustion analyzers where you take that dry soil, you burn it at a very high temperature, you measure the amount of carbon dioxide that it gives off. But so that's very accurate and very reproducible. The problem is organic matter is only part carbon. The rest is hydrogen, oxygen, and any other complexes that are on it. So you're only looking at part of organic matter. So we can look at fractions of organic matter. We can burn it off in bulk and accept the uncertainty. Right. So it's an indirect measurement, but it's good enough to get you certainly in the ballpark. And we'd like to see like 5 to 8%. Some of the stuff, we get from the Midwest it's surprising how low the organic matter is in those soils. Most of what we get from outside the region are from high tunnels, because that's one of our specialty packages, and those are so highly amended with lots of compost, lots of manure, and so forth, that we do run our regional test method on those.
That's a great segue. You mentioned you have been doing these high tunnel packages, and you and I have also emailed a little bit about the increasing number of heavily compost amended samples that you're seeing. How are you dealing with those samples and the uncertainty and the recommendations and all of that?
For the high tunnels, there's a tremendous range in management practices. Most of them are highly amended because you have to, you get this tremendous yield boosts in tunnels, 3 to 5 times what you get outside. And you have to feed that nutrient demand. So we've we've done a lot of regional research and coordination on this. So I think we're a little bit ahead of the rest of the country on this. But because there's such a range of management scenarios, some are really pushing a lot of productivity, a lot of amendments. Some of them are less so. You have newer tunnels that basically you're transitioning from open field production to covered production, and then there's tunnels that have been in production for 20 years. So it was quite apparent early on that one size does not fit all. So we've gone to a combination testing system. So some of these are so highly amended that they're up around 15, 20% organic matter. And you're starting to get into the range of container mix almost. And so what we've settled on is running both a field soil test that we would normally run for open field production We've added a direct check on nitrogen because you don't get the nitrate loss in a covered system that you do outside. And then we look at a total salt buildup in those soils because you don't have natural rainfall washing away accumulated nutrient salts, and they do tend to stratify or come to the surface by capillary action. So the top couple of inches have a really high salt level, and then the rest of the bed is more normal. So we've recommended that people remix before replanting. Keep an eye on the total salt level, and typically when you re-skin the tunnel, leave it open for several rainfalls, let the excess salts flush out, recover it, and replant. That's one of several different scenarios. But the other part of it is to look at the soil as a container mix. So we run what's called a saturated media extract, where you take the soil, as it comes in, you add water just to the saturation point, so all the pore spaces are full of water. And after an hour or so of equilibration time, you filter off the water and measure the nutrient content in the soil water, basically. So that's the short-term, immediately available nutrient content in the soil. This works, that's the standard method actually for greenhouse bench crops with container mix. So tunnels are kind of a hybrid, depending upon your management scenario, between field soil production and container mix production. So we run both tests. And then we trade off. The recommendation system is based primarily on the field soil test and then modified by the water-soluble nutrient content. So that's how we've evolved over the last 10 plus years for tunnels. And with some feedback from some of the deep compost mulch growers, that's how we're going to handle those soils as well. We had a little kind of a coordinating meeting earlier this year, and it was very educational for all of us.
Yeah, when you mentioned that you recommend if people have that stratified salt concentration, so you recommend remixing, is that, I mean, are you talking about how deep? Are you talking about tillage? And how does that work with the deep compost mulch growers? And with those deep compost mulch growers, how do you recommend they actually take their samples? Should it be, like a surface layer and then a separate mineral soil layer, or should it all be mixed? Or I'd love to hear about your conversations with those growers.
Well, that was primarily what I was interested in this meeting, was how do you sample these soils? And with no-till, there's always a problem with stratification, even with outside production, where you're applying really high nutrient content and especially phosphorus content with a new layer of compost every year. Same thing in tunnels. Well, first of all, to address no-till tunnel growers, your other option is to overhead irrigate and flush the salts back down through with water. Okay, that's specific to tunnels. Outside, you have natural rainfall. So the big concern out there was not salt buildup, but nutrient stratification. And one of the main feedbacks that I was interested in was when you dig down through a bed, if you do, is there, obvious layering like you would have, say, in a forest soil where you have an organic layer that's mostly compost and then the one that's mostly mineral layer? And what the feedback that we got was it's kind of a continuum from highly organic at the surface with a little, then some mineral mixed in and more mineral until you're mostly mineral down maybe a foot or so. So it's kind of a continuum. So there's no specific layering as such. So what we've settled on is to just sample a complete slice from the surface down maybe a foot, and send that in at.
Which is a little deeper than your typical soil sample would
Right.
be.
I mean, and this would be for raised beds, for instance. I think most deep compost mulch folks are using raised beds. Right. So just sample the top foot and don't try to separate it. We'll sieve out anything bigger than 2 millimeters when it gets here. And then we'll run like we would for a high tunnel. We'll run both season-long availability from a field soil test, and then we'll look at short-term availability with the saturated media extract and kind of treat it like we would a covered tunnel situation.
Are you seeing some of those systems actually have the pH go a little too far in the alkaline direction, even starting from an acidic soil?
Oh, yeah. And this is a problem with any high compost system. Finished compost, I mean, we run 200 or 300 a year through the lab here. Those finished compost is typically between pH 7 and 8. So there's quite a bit of liming effect, if you will, from compost alone. And so you're really high phosphorus levels, and usually somewhere between 7 and 8 on the pH. The problem with high pH is it limits the availability of some of the micronutrients, especially the metals. Iron, especially manganese, zinc. However, at high organic matter tends to chelate, is the term. It surrounds and protects those metals, keeps them available. So higher organic matter soils tend to kind of remediate or ameliorate the issue of limited availability at high pH. So it's kind of a trade-off in there. Yeah, I mean, some of those growers have been doing no-till for 15 years now, and they're doing just great. So our traditional interpretation of it's too much organic matter is maybe not true anymore. Different management situation. The problem that we see, the biggest problem that I see with compost is for people who use compost and little or nothing else. And this, especially with home gardeners, this is a problem where they're using, maybe a little too much compost. These are in tilled gardens. And why should I need to add anything more? Well, you do need to add additional nutrients because compost is not a complete nutrient source. It'll give you all the phosphorus you'll ever need, but it generally falls flat on nitrogen. And most growers, certainly commercial organic growers, know this, and they do supplement nitrogen. But it takes a lot of home gardeners, especially first-time gardeners, by surprise.
Was there anything else from those conversations with the deep mulch folks that you want to share?
I think, a lot of them were just trying to get into it. So we had some of the folks that have been doing it for several years. And, I believe most of them are supplementing nitrogen. They do soil tests and, adjust what you need to. Sometimes you don't have enough potassium. Phosphorus, as I said, is generally not going to be an issue at all. But basically, with those growers, we are, basically telling them to, we'll run your sample. We'll tell you what you need to supplement, but also we'll tell you what you don't need to supplement. That's kind of what's lost in a lot of cases is soil testing ultimately is supposed to save you some money on unnecessary inputs. So it's just as important. Yeah.
If there are growers out there in regions and their, regional labs don't offer this high tunnel or hybrid high tunnel field container mix test that you're talking about, would you recommend that they just get a regular soil test with the extraction that their regional labs use, or would you recommend they seek out a different test like the ones that you're doing?
For most growers, just a basic field soil test is sufficient. I'm trying to actively encourage other land grant labs to take up a high tunnel package, and some of them are actively working on it. Penn State, Kentucky, need to get a few Western labs on board to deal with this as well. But you can go with your normal field soil test that's appropriate for your region. And then, you can go, we have, all of our high tunnel guidelines are out on our website. There are fertilizer recommendation tables based on yield response, and it's primarily geared towards tomatoes and other heavy feeding crops, all the way up through to like 80 tons per acre equivalent yields. How much nitrogen, phosphorus, and potassium you need to supply just to cover what the crop is removing, is how those tables.
So based on the crop removal rates.
Yeah. So, so they can boost their recommendations based on that they're getting from their regional lab based on those tables. Now, for most tunnels, as I said, phosphorus is never going to be an issue. The one nice correlation between Malic 3, which is the most common commercial lab method, and modified Morgan is potassium is almost identical. So you can go specifically by our guidelines for potassium in modified Morgan and apply that directly to Malic 3, and it should be a transparent issue. They're both basically identical. They're all hugely different in phosphorus, and you get a little bit more calcium and magnesium from Malic 3 than modified Morgan. I don't think I mentioned Malic 3 also has a chelator in it, EDTA, that, and as I said, chelators grab metals and keep them water soluble or available to plants, as in organic matter chelating metals. But when you add a chelate to the extracting solution, it grabs a lot more copper, iron, manganese, and zinc. So you're getting a lot more of those micronutrients in Malic 3 than you would in either of the Morgan extracts.
So I'm wondering about salts. So that seems like a key part of your high tunnel package. And if I'm assuming you just measure that in electrical conductivity, and I'm wondering if it's something that needs to be measured or if it's something that people can just observe. Like if you have a salt problem, do you actually see an accumulation of salt on the surface, or can you have sort of an invisible salt problem?
Usually you're going to see crusting at the surface, on really high salt levels. That's that stratification, especially if you have beds sitting over the winter, static. You're still having evaporation over the winter. Although a lot of tunnels, they're doing winter greens, so you may or may not see that. It's usually most labs will have a field soil test, but most labs also do a greenhouse, what's called a greenhouse media test, which is that saturated media extract. So if you're really worried about it, you could ask to have both tests run. I mean, they're going to send back, assuming that it's some sort of a greenhouse container mix still, that's how that is generally reported and interpreted, and looking at water soluble nutrient levels, but it will give you the total EC, electrical conductivity from all the water soluble nutrient content.
And of the high tunnel samples that you see, just sort of guesstimate what percentage would you say have electrical conductivity that's a little too high or above ideal?
Probably 25 to 30%. It depends on where they are in the growth cycle. Some of them are static over the winter. Some of them have winter greens, and then they go back into high heat crops for summer. And so generally they're, the high heat crops are obviously the higher nutrient demand crops. So it depends on if it's just after an application of compost or manure, then you're going to generally have a pretty high level of soluble salts. And generally, if they're much above like a level of 4 on the saturated media extract, we're going to start telling them that you need to either flush the salts with overhead irrigation or uncover if you're at the point where you're going to swap plastic. Or the other thing you can do is bring in more soil, or if your organic matter is low, you can add some peat moss, basically mix that in and dilute out the salt level, get it down to a level that's not going to be such an osmotic gradient against the plant trying to pull in water against all that salt gradient. That the plants don't have drought stress.
One final question, or I don't know, maybe second to last question. We've talked a little bit about some of the limitations, but what are some of the limitations of soil testing?
Well, I mean, the first limitation, of course, is we're just looking at nutrient levels and gauging that based on what we consider to be through calibration research, what's an ideal level, and then basically telling you what you need to supplement your current levels based on what you're growing, and your management scenario. But that doesn't cover issues like even like soil drainage. This past growing season, where it never stopped raining, we're getting in a lot of samples from people that had terrible problems with plants just not growing. Either they drowned altogether, or they didn't have enough nitrogen throughout the growing season because there was so much leaching loss from applied nitrogen early in the season. So it doesn't address things like soil drainage. It doesn't obviously address disease or insect issues. It's just one part of the overall picture of crop production. And I think most commercial growers obviously realize that, and perhaps some home gardeners don't. But as I said, it's an indexing system, and one of the nice things about soil science, what's kept me in it, is there's always something new. There's always something you didn't anticipate. It's such a complex biogeochemical ecosystem that we try to understand more through research and feedback from growers, but there's always something more that you just didn't consider before. So it keeps it interesting. That just as an aside, but so there's a big emphasis now on soil health, and we could probably do a whole nother hour on that. But right now we're trying to figure out what we should be measuring for soil health. What's the most informative in biological and physical parameters in soil health testing that really that's still very much in development. It's been for 10 or 15 years now, the subject of pretty intense research and trying to figure out which test methods actually have some meaning in assessing and managing soil health. And so that's one area that we're still, it's taken 100 years basically to pretty well refine nutrient management, soil fertility. And now there's a big push to ramp up, that interpretation for overall soil health assessment and soil health management.
Yeah, that was going to be my next question, so I may just skip it. It was sort of what's the future of soil testing, and so refining those soil health tests. Well, I really appreciate your taking the time to chat today, and I learned a lot, and I know this is starting to be the busy season for you, so I wish you the best of luck with that.
Okay.
All right. Thanks, Bruce. Thanks for listening, everyone. And thanks to the crew at the No-Till Market Garden podcast for letting me have these conversations. I used to get really nervous before them, and I still do. But I also really look forward to talking with these amazing guests. So it's fun. Thanks to all the guests. Thanks to the crew. Thanks to you all for listening. I hope everyone is having a great season.
All right. I hope you enjoyed that episode. Very fun to have Natalie back, I must say. Real quick, some things that we have going on. Make sure you are following along on YouTube. Last week, we got a farm tour of Mountain Roots Farm and a thorough look into the wash pack station there from Paul Wargo. This weekend, we are talking contouring versus terracing with Spencer Rudolph of Sage Hill Ranch Gardens there at YouTube. Far and away the steepest farm I've ever seen in person. Find that channel by searching No-Till Growers on YouTube. We'll put a link in the show notes, and also linked in the show notes is our shop where you can find things like the Living Soil Handbook and hats and other ways to support our work. Buying those things through us helps to support these podcasts and our videos and all the things, and helps keep this information free and open to anyone and everyone. Alternatively, you can join a whole bunch of new supporters through patreon.com/no-till-growers. Who get a bunch of discounts from various companies on seeds and footwear and all sorts of other goodies, but also get their input on the kind of content we create. That Patreon page is the absolute lifeblood of our work, and we dearly appreciate each and every one of you. And at a certain level, or if you just bump up from one level to another, you get a shout out on the show. So big shout outs this week to Shell Shelton, Mark Ravenel, Doug Wilkes, Lee Shelley, Brian McCarthy, Larry Shepard, Spencer Carter, Marsh and Cindy, DP, Kat Brannigan, Tyler Rollins, Hank Zecca, Chris Yates, Jill Crosby, Stephen Wilder, Scott Roser, Norsk Guard Farm, Sean at All About the Garden, Lori Britton, Joseph Sanguinetti, Alex Savatsky, Pear Tree Hill Farm, Stephen and Alex, Stephen Smith, Alberto Diaz, Jason Ruel, Scott Harris, Earth Care Farmer Jane Murner, Derek Page, Claymont Grown Up Farm, Bob and Ann Patton of Hexhamshire Organics, Jared Kirst at Rivendell Farm, Dan Breezebois, Steve Larson, Fiona and Donnie of Firefly Farm, Jen Lawrence, and Cameron Prybol. Huge shout out to whoever supports us in whatever way that you can. Otherwise, thanks for listening, y'all. We'll catch you next week. Bye.